And for the beginning, let's recall what we did last time. So we were studying for the last 2 weeks differential equations. We were studying only ordinary differential equations of this type. We have a function of dependent and independent variable t and x, and also derivatives of the dependent variable with respect to independent one. So last time we went over a few methods for solving such ODEs analytically. So meaning we didn't use any numerical approximations, but we were able to solve some types of such equations directly. So let's recall which types were those. So the first type was first order ordinary differential equation. So first order, it depends on the derivative, which is only the first derivative. That's why we call such an ODE first order. We said that if we have a first order differential equation, then we expect general solution to be a family of one parametric family of curves. Increasing the order increases the number of those free parameters. So if we had two second order differential equation, then we would expect a general solution to be a two parametric family. And we're talking about a separable differential equation whenever this right-hand side, which is a function of t and x, so dependent and independent variable, is in fact the product of two functions. One depends only on t and the other depends only on x. In this case, we can separate variables. So we put all x's on one side, all t's on the other, and integrate both sides. Of course, the functions g and f, so in this case, a function f and 1 over g must be such that they allow exact integration. So we have to know what is the indefinite integral of 1 over g and what is the indefinite integral of f. Here are a few examples. And then we generalize this to first order linear differential equations of this type. So if you observe this line 9 and compare it to the separable case, the difference is that here in line 9 we also add some function of t, some function of the independent variable to our differential equation. So if we put g to 0, then we get a separable differential equation. But if g is not 0, then it's not separable. So how to solve such a first order linear differential equation? It's called non-homogeneous. We have to solve the homogeneous part. So we first put g to 0, solve the homogeneous part by separation of variables. And then we have to find, so the general solution of the homogeneous part is some constant times some particular solution. So it's enough to find one particular solution of the homogeneous part and multiply it by a constant. Those are all solutions of the homogeneous part. And then we need to either guess one particular solution of this non-homogeneous equation, or obtain it by a variation of constants. So variation of constants is a technique which changes this constant in the homogeneous equation to the function of the independent variable. So in this case, c of t. And then we just plug in this form into the initial equation. And it turns out that we can explicitly compute one particular solution. So now we have a homogeneous solution. So the solution of a homogeneous part, we guessed or obtained one particular solution. And then all solutions of these first order linear differential equations are just such sums. So sum of the homogeneous solution plus a particular solution. To determine this C, we have to know one additional condition. So either the value of x at some time point. So either at the beginning of the time interval or anywhere in between. So we need one additional condition to determine C. Here is one real life example. So Newton's second law. You all know it, that Newton's second law tells us that force is mass times the acceleration. When we throw a ball of mass m vertically into the air, if we don't assume any other force, only Newton's only the gravitational force, then the equation which describes the motion of the ball is this one. So m mass times the acceleration is the force. So the force is minus mass times gravitational constant. And so this is first order differential equation. The dependent variable is velocity and the independent one is time. And we can easily solve this equation. So velocity is linear function of the time. However, if we add also the resistance of, the resistance of air, so the resistance of air is modeled by such a force. So force is minus some constant times the velocity. And then the motion, the differential equation which describes the motion of the ball thrown vertically into the air is that one. So mass times acceleration. Acceleration is just the derivative of the velocity, is minus this gravitational force, and also minus this air resistance force. And what we get is a linear differential equation in dependent variable, which is velocity, and the independent variable, which is time. And also this equation is easily solvable. In this case, the velocity is not linear function of t, but it is exponential function of t. So velocity depends on the time exponentially. So this graph represents the motion of the ball without assuming air friction, and the second graph represents motion of the ball assuming air friction. So this blue line is the velocity, and this orange curve is the position. So you see that assuming no air friction, the motion is symmetric. So ball goes up, reaches the highest point, and then returns back to the initial position, and everything is symmetric. However, when the velocity, when we also have air friction, then the motion is not symmetric anymore. Velocity changes exponentially with respect to time, and also the motion is not symmetric. So it takes more time to fall than to reach the highest point. So here we reach the highest point this time point, and then the ball falls to the round. So for falling to the round, it needs more time. So this is one real life example of the linear differential equations. Then we studied, so at the end, we studied homogeneous differential equation. This is also one type of the equation which can be analytically solved. So whenever we have a differential equation, where the derivative, the first derivative, is a function of not t and x, but a function of the quotient between the dependent and the independent variable. So whenever we can rewrite the right-hand side in this form, we can introduce a new variable u, which is x over t, so the dependent variable over the independent one. And so then the dependent variable is u times t. And then we can plug in x derivative into the initial equation. And instead of x over t, we simply write u. And what we get is a linear differential equation. First order linear differential equation in the new variable u, and the independent variable is still t. And we know how to solve such a differential equation. So the example for this homogeneous type of nonlinear differential equation was the problem of determining orthogonal trajectories to the family of curves. So we were given, if you recall from the end of last lecture, we were given a family of curves described by some equation. So it was we had a family of circles with centers on one of the axes. So such a family can be given as a solution of such an equation, if you recall. So for example, if you have a family of circles going through the origin and have centers on the y-axis, they're just the solutions of this equation: x squared plus y squared minus 2ay equals to 0. So the solution, when we vary a, this a is a parameter, so when we vary a, we in fact move the center of the circle up and down the y-axis, because we can rewrite this equation as x squared plus, and then in the parentheses, y minus a squared, and then we have e equals to a squared on the right-hand side. So the picture is like that. So this family is this family of blue circles. And we would like to determine the family of curves which are perpendicular to, in every point, to some curve in our initial family. And it turns out that the family of those curves is just the family of circles with going through the origin, and the centers lie on the x-axis. So these are these green circles. So how to obtain the family of orthogonal curves? We can get rid of this parameter a from this differential from this equation determining our initial family by, so we did this last time, so we just differentiate the initial equation with respect to x, so with respect to the independent variable, express a if it's possible to do it. And when we express a, we can plug this into our initial equation and in fact get a differential equation where we don't have any parameter a present, only y, x, and y prime. And then to obtain the perpendicular curves, we just replace y prime with minus 1 over y prime. Why is this true? Because you know from calculus or even from high school that two lines intersect at right angle if their slopes are perpendicular, are inversely proportional, and they have different signs. So if the slope of one line is y prime, then the slope of the other line must be minus 1 over y prime. So we just replace this in our equation, and we get a differential equation determining the family of orthogonal curves to the initial family. And in this example, so if we do this, if we start with blue circles, we end up with those green circles. And so why is this an example of a homogeneous differential equation? Because when we express y prime out of this initial family by this algorithm, what we get is y prime is minus x squared minus y squared over 2xy. And we see that this can be rewritten as minus x over 2y plus y over 2x. And we see that this right-hand side is really a function of the quotient between y and x. So we do this substitution. Y is u is x, y over x, and then rewrite the equation, our differential equation, as a linear differential equation in u and x. So, and I would like to add something to this. We did this last time at the end, but I changed the problem. So instead of taking for the initial family, this family of blue circles, I took for the initial family, the family of green circles. And then our differential equation was, in fact, that one. So y prime is 2xy over x squared minus y squared. And at first sight, it didn't look it didn't look possible to translate such an equation into the homogeneous form. So into such a form that the right-hand side depends only on the quotient between y and x. And then we change the problem to the one which is on slides. However, the problem is too symmetric to believe that one problem would be solvable, but the other not. So it's too symmetric to say, if we start with the blue family of circles, then it's possible to obtain a solution by this method. However, if we start with green circles, it's not possible to obtain the family of the family of solutions by this method. So it doesn't make it doesn't look plausible to believe that one would be solvable but the other not. And the first thing which I would like to show you is that even if we have such an equation, y prime is 2xy or x squared minus y squared, it's still possible to transform it into the homogeneous form. So this is the first thing which I want to show you. So we have y prime is 2xy over x squared minus y squared. So how is this a function of y over x? So we would like to show that this is a function of y over x. In the case when numerator and denominator are swapped, it's easy to see. However, here we believe this is true, and we will show that this is really true. So let's just write that u is y over x. And from here we express y, and we get u times x. And let's plug this into our equation. So y prime, this is u prime x. Recall that u is a function of x, so we have to differentiate by using product rule. So u prime x plus u times derivative of x, which is 1. This is left-hand side. And the right-hand side is then 2 times x. And instead of y, we write u times x. And in the denominator, we have x squared minus ux squared. And let's rewrite the right-hand side a little bit. So we have in the numerator, we have 2x squared u, and the in the denominator we have x squared times 1 minus u squared. And now we see that x squared and x squared cancel out. So what we get is 2 times u over 1 minus u squared. So altogether, we see that we really have a homogeneous differential equation. And now it is a linear one, so it can be solved explicitly. So yeah, by the nature, by the symmetry of the problem, we can infer that also if we swap y and x, this should still be the same hard. So the problem should still be the same hard. So if one can be solved by translation to homogeneous differential equation, then also the other one should be. Okay, this is where we stopped last time. For today, the plan is that we will first look at another differential equation which can be solved analytically. It's called so-called exact differential equation. And then I will show you one theorem about the existence and the uniqueness of solutions. So we have differential equation y squared is some function of x and y. And before we even try to solve it, we would like to know if the solution exists, and if it exists, how many solutions exist. So given, and also we are given some initial conditions. So without initial condition, we know that the solution is not unique, but let's say that we fix some initial condition, then we expect that there should be a unique solution, and we will say something about the existence. And the existence, of course, depends on this function f. Okay, this will be the second thing. And the third thing will be, in fact, numerical methods for solving differential equations. So differential equations are important, really important in real life. Whenever we model some dynamical process, such as weather changes or changes some physical quantities, or we will see biological phenomena, everything can be described by the use of differential equations and more generally systems of differential equations. Usually there are more variables, so we should have some system of differential equations. And in practice, those systems are not solved analytically, but numerically. So we are trying to find a solution which approximates the real solution within some good bound. And we will see the numerical methods used. In fact, you've seen two methods already at the lab sessions. So the first is Euler's method, and much more accurate method, which is also much more used in computers, is so-called Runge-Kuttas method. And I will show you a little bit behind this Runge-Kuttas method. So a little bit behind what's the idea, why does it work, and why it's so accurate. So it's much more accurate than the Euler's method. And then the last thing today will be systems of differential equations. So up to now, we've studied only one differential equation. And we will see those numerical methods first for solving one differential equation. But then we will see that they can be generalized to systems of differential equations. So we have y1, y2, and so on, and x1, x2, and so on. So more variables and more dependent and independent variables. Okay, this is the plan for today. Is there maybe some question? Okay, if not, then let's first look at this exact, so-called exact differential equation. This is another differential equation which can be solved explicitly, analytically. It's very connected with what you know from analysis, so from the chain rule from analysis. So we have, again, first order differential equation. X prime is a function of t and x. And let's now recall, so we have a function, some function u of two variables. So we have a function, let's recall in the notation of calculus so that you will easily recall, you have a function of two variables which maps into reals. It has variables x and y. They are not connected, they are independent. So f of x and y. And so what is the change in this? So what is the change of f? So yeah, let's recall. So we have a function. Let's say we have a function of two variables, so x and y, and its graph is some surface. This is the graph of f. And now we have some point here in the domain. So this is some point x, y. And we would like to know how much the function value changes if we go in some direction. Let's say direction is e, is determined by the vector e. So how much does this function value changes if we go from point x, y in the direction of this direction determined by the vector e? So probably you recall from calculus that we should calculate the directional derivative of f in the point x, y in the direction e. So we were writing this as f and then subscript e, vector e, x, y. And you can recall from calculus that this is gradient of f in the point x, y times dot, so dot product with this e. So this is nothing else than the partial derivative of f with respect to x times e1. If so, here we write vector e as e1, e2. So it's partial derivative of x with respect to x times e1 plus partial derivative of f with respect to y times e2. So this is the formula for the directional derivative. And if we say that, if we take for e, let's say that e is some change in x, and then some change in e1 is some change in x, some small change in x, then e2 is some small change in y, then we can rewrite the formula above that the function value changes for the product of the derivative of the partial derivative of the f with respect to x times this change in x plus partial derivative of f with respect to y times change in y. So this is another way of expressing this formula for calculating directional derivative. And if we send those changes in x and y to 0, we in fact get so-called differentials. So differentials are just limits of the changes in both directions. So we can rewrite this formula by the means of differentials. So differential of f is then partial derivative of f with respect to x times differential of x plus the same for the other summand. So you can understand this formula just by saying that this df, dx, and dy mean that those changes are small. So we have here above, we have usual changes in f, changes in x, changes in y. If we want to emphasize that they are small, then instead of delta, we write these and call those these differentials. Okay, and here on slides, we have the same formula written only in other notation. So we have our function f is on slide is u. Then the independent variables are t and x. However, here in the derivation, we had x and y. So it's on slides, we have this formula, which is basically what I've just explained, only that the names of the variables and the name of the function is different. Okay, and let's look again at our differential equation of first order. X prime is f of t and x. We know that we can write this x prime, as dx over dt. And then we can write, if we introduce this dx and dt, then let's say that this first order differential equation can be rewritten as this form. Not that, let's say, but it's always possible to rewrite it in this form. It's some function of t and x times differential in t plus some function of t and x, which is here named n, times dx is equal to 0. And if you compare here, so let's compare. So this with the differential of u, what we notice here is if this m of tx, if we try to say that this m of tx is in fact partial derivative of u with respect to t, and then this n is partial derivative of u with respect to x. So if this is true, if we can find such u which satisfies those two conditions in boxes, in green boxes, then what we have here is that so this equation 1 implies that differential of u is equal to 0. So under the assumption that we can find a function u such that its partial derivative with respect to one variable is m, and partial derivative with respect to the second variable is n. In this case, our differential equation is in fact du is equal to 0, because on the right hand side of the differential equation we have 0. But what does this mean? This means that the solutions of our differential equations are just the level curves of the function u, because du is 0. So the solution of this differential equation is that u must be equal to some constant c, for c in real numbers. And this is what gives us explicit solution. So this is the family of curves which solves explicitly our initial first order differential equation. So if we are able to find u, I mean, if this u exists, then since du must be 0, the solutions to this are just level curves of this function u. So u must be constant if we want that differential of u is 0. If it doesn't, on the solution, the value of of u shouldn't change, which means that it's constantly equal to some real number c. Of course, for most equations, it won't be possible to find u. But maybe if this is doable, then we know how to solve the differential equation explicitly. And we will see one example. Let's look at one example of this technique. So when will this be doable? We would like to plan, does u satisfying partial derivative of u with respect to t is a function m, and partial derivative of u with respect to the second variable is n. So does such u exist? What you know from calculus that if the function is twice differentiable and if all second derivatives are continuous, then it doesn't matter in what order we take those derivatives. So derivative of u with respect to t and then with respect to x should be the same if we to the case where we first take the derivative with respect to x and then to t. So this condition should be fulfilled. It shouldn't matter in what order we take the derivative. So we only said this, we didn't prove it because it would require quite a lot of technicalities, but this is what should hold. So in our case, this implies that the derivative of m with respect to x should be the same to the derivative of n with respect to t. Because if m is ut, then utx is mx, and if n is ux, then n sub t, so n sub t, I mean the derivative of n with respect to t should be uxt. So if this condition is satisfied, then we know that function u exists. And how we get it, we just take, so how we get such u. So the first, this equation u ut is equal to m implies that u must be indefinite integral of m with respect to t plus some constant, which is, but here not a constant, not constant for all x, but only a constant with respect to t. So it should be some constant with respect, which can still be a function of x, because we know that taking the indefinite integral, it is unique up to the constant, but this constant only this means that it's only the constant with respect to the variable, the integrating variable. So we can still have the dependence to the other variable in this constant. And the same for for the other case. So ux is n, then u is integral of n with respect to x plus some other constant. But in this case, the constant should be, again, independent of x, but it can depend on t. So altogether, we take all those terms, all different terms in both, from both right sides together. So uxt is then sum of all different terms on the right side, on both right sides. This will be more clear on an example. So our example is the following. So we have a differential equation x plus y times e to the power of 2xy plus x times e to the power of 2xy times y prime is equal to 0. To try if this differential equation is exact, we have to rewrite it into the form with differentials. So y prime, this is dy over dx. So what is our m? So we have x times e to the power of 2xy times dy on one side, and then plus, so in fact, on the other side we have, or we can just say that we multiply here by dx and we will spare one step. So we multiply by the dx, and what we get is plus x plus y times e to the power of 2xy dx is equal to 0. So this is the candidate for m. I mean, this is m, and this is n. And what we have to check, if before we start calculating the potential function u, we have to check whether this condition is satisfied. So the derivative of m with respect to x should be the same to the derivative of n with respect to y. So this is the condition to check. And what is the derivative of n with respect to x? So it is, by the product rule, it's derivative of x, which is 1 times e to the power of 2xy plus x times the derivative of e to the power of 2xy, which is 2y times e to the power of 2xy. And on the right side, we have the derivative of n with respect to y, which is, so x disappears, so this term x disappears, and this second term is in fact the same, the same form as m, only x and y are swapped. So we can just rewrite without calculating, we can just rewrite this left-hand side, only we swap x and y. So e to the power of 2yx plus y times 2x times e to the power of 2yx. But we see that this is in fact the same. So the condition which we have to check to see if the potential function u exists is satisfied. So this is really exact differential equation. Let's finish with this example before we do a break. So now u, the candidate for u, is integral of m with respect to y plus some constant which is independent of y, so plus some constant in x. So what we get is, so integral of x times e to the power of 2xy dy plus some constant of in x. So x is independent of y, so this is x, and integral of e to the power of 2xy, this is e to the power of 2xy, and we have to multiply by 1 over 2x plus cx. So it is 1 over 2 times e to the power of 2xy plus cx. This is the candidate for u. You see now, so one part of u is determined. This term is already determined, but we would like to determine also this function of x. So we don't know what's this function of x. We have to determine it, and this will be done from the other integral, so from the integral with respect to x. So on the other hand, uxy should be also the integral of n dx plus some function of y. So this is integral of our n was x plus y times e to the power of 2xy dx plus dy. So this is the first term, x integrated with respect to x is x squared over 2 plus, and now y is independent variable, times again e to the power of 2xy, and here is also a constant 1 over 2y plus dy. So again, y and y cancel out. You see that we again get this term e 1/2 times e to the power of 2xy. So these terms are the same. Then x squared over 2 is a function of x. So this is in fact part of c of x. And then here we have also a function of y, but this function of y was already covered. So it is already covered, because this function of y, should occur here, but should occur here, but this part also occurs here. So this function of y is in fact already covered by the first term. So the final solution uxy is then 1/2 times e to the power of 2xy plus x squared over 2 plus some function, plus some constant c. C is a constant. There indeed cannot occur any other term in x on y, because if there was another term in x, it should appear in this line. But if there was another term in y, it should appear in this line. So we really have all different terms of x and y present, but we also allow this constant c, because this constant c, this always appears unless we have an initial condition given. Okay, this is all for exact differential equations. So now we make a break. So before we do a break, is there any question regarding what we did this hour?
Yes, I have a good question. Can you please repeat why is this derivative of m with respect to x should be equal to the derivative of n with respect to y?
So under the assumption, so if really derivative of u with respect to t is m and derivative of u with respect to x is n, if this is true, then those mixed derivatives, mixed second derivatives should be the same, because we are searching only a function which is continuous and twice differentiable. So we are searching only for nice solutions. So continuous and twice differentiable. And under the assumption that the solution is continuous, we know that these mixed second derivatives should be the same, which means that here if we take the derivative also with respect to x, this is the same as taking the derivative of m with respect to x. And if we take here derivative with respect to t, this is the same as taking the derivative with respect to t of n. And this means that those two must be equal. So m taking the derivative of m with respect to x and taking the derivative of n with respect to t should be the same. This is this condition. This condition implies this equality. For this condition, we need that u is continuous, so twice differentiable and continuous. Does this answer your question?
So if this isn't true, then this means that our function is not continuous.
So if this is not true, if we are searching only continuous functions and this condition is not doesn't hold, this means that our equation is not exact. It's not of this form. So then it only means that the solutions of those equations, of these differential equations, are not level curves of some potential function u.
Okay, now I understand. Thank you.
Okay. Not every differential equation is of this form. So there are only a small portion, really small percent of functions are such, differential equations are such. So if this is not true, then this only means that u doesn't exist. But differential equation can be still solved in another way.
Okay, thank you.
Okay, let's do a break and we start 10:23. So last hour, we looked at the technique of solving exact differential equation. So exact differential equation is differential equation which has a potential function u. So this is a function for which we know that the derivative with respect to x is the function which appears the differential of the other variable, and the derivative with respect to the other variable is the function which occurs with the which occurs with the differential of the first variable. And before we go to numerical methods for solving differential equation, which will be the most important tool in this course, let's say something about the uniqueness and the existence and uniqueness of solutions. I will show you the basic theorem in the theory of DEs. We won't prove it. I will only comment on its statement. So this is so-called Littlewood-Picard's theorem. by the authors of this theorem. And we are given the first order differential equation together with the initial condition. So y prime is function of x and y, and we know the value of y at some point x naught. And we are searching for the solution on the rectangle D. So I will draw here this rectangle. So in x naught, we have the value is y naught. This is a point through which the solution should go. And then we move for a in x-axis to the left and to the right. So we have x naught minus a and x naught plus a. And the same for y, but we move for b in both sides. So we have this rectangle. And we would like to find the solution to our differential equation in this rectangle. So what are we searching for? We're searching for a function, for a continuous function passing through the point x naught, y naught. And this function y should satisfy our differential equation. So what can we say given our function f? We know that the function f is continuous and differentiable with respect to the second variable with respect to y on this rectangle. So f continuous on the rectangle D, and differentiable, so the derivative of f with respect to y exists on D. This is our condition. And we would like to know whether this differential equation is always solvable. And what the theorem by Littlewood and Picard tells us is, yes, this differential equation is always solvable. So y always exists, but maybe not on the whole rectangle. Maybe the solution exists only on some part of the rectangle. So the theorem says that there exists some interval around x naught on which the solution exists. So there exists alpha such that on x naught minus alpha to x naught plus alpha, the function y exists. And moreover, it doesn't only exist, it is unique. So y exists and is unique on some subinterval x naught minus alpha, x naught plus alpha. So this is a subinterval of the initial interval x naught minus a, x naught plus a. And this alpha can be explicitly determined. So this alpha is minimum between a. Of course, it can be bigger than a because our function f, by assumption, our function f is given only on this interval between on this rectangle, so we cannot go over this rectangle. And then we also have two other bounds. Here, I won't write them again because they are written on the slides. So one bound depends. So this one bound depends on the maximum of the function f, and the other bound depends on the maximum of the derivative of f with respect to y on this rectangle D. So let's say here a tilde and a prime. I won't prove this theorem. So what you have to remember is that under these conditions, that f is continuous in differentiable and differentiable with respect to the second variable, then the solution indeed exists for every such f, and it exists. It is unique on some subinterval of the initial rectangle. So I will only give you the idea how to obtain those two other bounds, so that you will at least get a little bit of taste for those two bounds. So we have here y prime is f of xy. It's nothing deep. So those two bounds are nothing very deep, but they are technical. So we won't go over the whole derivation. Only a taste of it will be given. So let's integrate both sides of our differential equation with respect to x. So this is our differential equation. Let's integrate it from, let's say, x0 to some x. And also, so with respect to x, we integrate, and also the other side. So from x0 to x dx. On the left-hand side, so what is the integral of the derivative of y? Integral and differentiation, integration and differentiation are inverse operations. And so we know that the left-hand side is y of x minus y of x0. Here we also used the fundamental theorem of calculus, which says that the definite integral is in fact one of the indefinite integrals. That's why we can just easily integrate the left-hand side. While on the other side, you can just rewrite x0 to x, f of xy dx. And what we know, since our solution must live in this rectangle, we know that the difference between yx and y0 must be at most half of the side of the rectangle. So it must be at most b, because y of x must be somewhere on this line, and y0 is on the middle, in the middle. That means that the difference between yx and y0 is at most half of the length of this side, so it's b. So we know that this must be smaller than b in the absolute value. So the condition is that the absolute value of this is smaller than b. And now let's do some estimation. So we will estimate this part. So we know that if we have an absolute value of the integral, then this is smaller than the integral of the absolute value. Why? Because if f is always positive, then absolute value outside or inside the integral is the same. However, if f changes signs, then if we integrate the absolute value of f, we will get more than if we integrate f and then take the absolute value. So this is smaller than the absolute value of f. But for the absolute value of f, we have here on the slide, we have this m. So this capital M denotes the maximum of f on the rectangle D. So this absolute value is smaller than maximum of f on the rectangle. So this definite integral is then smaller than the integral from x0 to x of this constant m. If we know that the integral of m is smaller than b, if we fulfill this condition, then also this condition at the beginning will be true, because we estimated the left-hand side with something which is bigger, and if this bigger is smaller than b, also this initial number will be smaller than b. So integrating constant m from x0 to x is m times x minus x0 if x is bigger than x0, otherwise it's absolute value from x to x0, and this is smaller than b. So this is smaller than b. The condition is that x minus x0 is smaller than b over m. This means that x must be on the interval from x0 minus b over m to x0 plus b over m. And what we did, what we obtained is in fact the second bound on alpha. So you see the second bound, alpha must be smaller than a. This is because it should be within our initial rectangle. Then it should also be smaller than b over m, because if it's smaller than b over m, then we know that this condition will be fulfilled. Okay, and the third condition is obtained by similar reasoning. We need some another theorem which is not very deep, but it will took us another half an hour to explain it. So we won't I won't explain how to obtain this third bound, but the third bound is 1 over maximum of the derivative of f with respect to y. If someone is interested, you just Google Littlewood-Picard theorem, and you will see also the derivation of this third bound. It's short, but it requires this additional theorem, which we won't go through. So the message of this theorem is that, yeah, we are not, when we pose such a differential equation of first order with initial condition, we always have a solution. So such a differential equation, such a system is always solvable, but maybe we should shorten, narrow our interval a little bit.
So these conditions for alpha are because we don't want to fall out of this rectangle.
Yes, this first condition, these first two conditions are because we don't want to fall out of our rectangle. However, the third condition, in fact, gives us that the solution exists.
Ah, okay. Thank you.
The third condition is not doesn't only take into account that we should stay within the rectangle, but this third condition really ensures that the solution exists. Okay, I can write what does this third condition, why we need this third condition, so that it won't stay mysterious. So we are searching for a solution in continuous functions. So we are searching for a solution y of x, which is in fact a continuous function from the interval x0 minus some alpha to x0 plus alpha. We don't know what is alpha yet, into the interval x y0 minus beta, y0 plus beta. We can, so these are our continuous functions, and we write the space of continuous functions. Usually the space of continuous functions, maybe you remember from calculus, it is C, and then we say what is this initial interval and what is the codomain. So these are our space of continuous functions from this interval into this interval, and we are searching for the solution from the space of these functions. So this is a vector space. Moreover, we can equip it with a norm to become a normed space. I don't know whether you had normed spaces in linear algebra, probably you did. So we can equip this space with norm of the function. Usually it's denoted by this infinity. It's supremum norm. It is just maximum of f on this in the domain. So x goes, so maximum of the absolute value of x from the domain. So this is a norm in our C. I will write it as C. Norm means that it's positive. It means that it respects homogeneous, so it's positive homogeneous. So alpha, norm of alpha times f is absolute value of alpha times norm of f, and it also respects triangle inequality. So norm of f plus g is smaller than norm of f plus norm of g. And now I define an operator, a linear operator, let's say L, which maps from C into, so it maps from C into C. Maybe I will have to a little bit change the codomain. We will see. So this C F is mapped into phi. Let's say phi, because f is already used for our function in the differential equation. So phi is mapped into the integral of f x phi dx. And the integral is from x0 to x. So what is the idea? Yeah, the codomain is correct. So why I defined the operator L like that? Because we see that if the solution of our differential equation exists, then the solution is exactly the integral of f, because y prime is f. So if we are searching for y must be then the integral of the right-hand side. And the right-hand side is exactly f. So this, the right-hand side should be y. So we are searching for y. So we are searching for y such that L of y is equal to y. So L of y, this is by definition x naught to x of f of x, y. And this should be equal to y if our differential equation is solvable. Okay? And here comes this part which I cannot explain in very quickly. So this L, so this is a linear operator. So we know that L has a fixed point. So you see what fixed point is. Every function which is mapped by the operator into itself is called a fixed point. So in this case, we are searching for y, which is a fixed point of this operator. And we know, this is some theorem, that such a linear operator on a normed space has a fixed point if it's a contraction, has a fixed point if it is a strict contraction. This means that norm of Ly, so this infinity norm, supremum norm, should be smaller than supremum norm of y. And here it shouldn't be only smaller, but it should be smaller than some constant which is smaller than 1. So it's some constant smaller than 1, and this c, so it's a constant smaller than 1. So we have a linear operator L. If it has a fixed point y, then it is the solution of our DE. And the theorem says that such an operator or normed space has a fixed point if it is a strict contraction, meaning that it always, so it takes some function, and the supremum norm of the mapped function should be smaller than the supremum norm of the initial function. And this C is a contraction constant. And from this condition, one obtains the third bound. So this C, this contraction constant, is connected with this third bound. So if we take for alpha, if we take 1 over the supremum norm of the derivative of f with respect to y, then this will be appropriate constant C for the operator L to be a contraction. But so this is the idea behind, but how does one see this? I will leave it to you if you are interested. It's not very long, but it's a little bit of work. As I said, just Google Picard-Littlewood theorem and you will see a derivation. Okay, is there maybe any other question? Okay, if not, then we finally come to the core topic of solving differential equations by means of computers and by means of this course. So numerical methods for solving differential equations. As always by now, we have a first order differential equation with initial condition. It's called an initial problem. Whenever we have initial condition given, then we are talking about initial problem. And the idea will be to approximate the solution using some geometrical, some geometry behind. And I will just draw one example and explain on this example, so-called Euler's method. You've already seen this method in this week's lab session. I will tell you a little bit more about the error you make using this method. Otherwise, it's really easy to implement. And then we will generalize it to the more well-known, I mean, to more used Runge-Kutta method. So we have a function y. So we are searching for a function y. Let's say that we would like, we have this differential equation, y prime is f of yx. The solutions to these equations are curves. I will just draw a family of curves which solve this equation. Now I don't use the initial condition yet. So those are the solutions to our differential equation. And now we will use the initial condition. Let's say that in x0, the value is y0. So it's y0. So we are in this point, and we would like to determine this curve. So this upper, the highest green curve. But we are not able to analytically solve this equation. What we can do is to calculate the derivative. So we can compute the derivative of y in x0. It is just f of x0, y0. This function f is given. We know x0, we know y0, so we can compute the derivative. When we have a function and the derivative, we in fact know the tangent to our curve. So I'm drawing here the tangent to our curve. So we will approximate our solution. We will move along the tangent for some step size. And let's say that the step size, it's usually fixed in advance. It's h. So we will move from x0 to x0 plus h. And we will approximate our solution by moving along this tangent, and we will come to this point. So this is our approximation. So in x0 plus h, we have not y1, because if we had y1, y1 exactly would be this one. So this would be y1. We didn't get y1. We got only approximation of y1. So this is y1 prime, let's say tilde. What we did, you see, we moved to another curve in our family of solutions of our differential equation. And we would like to, so we already did some mistake, some error. From here on, we would like to follow this second curve. But again, we don't know how to explicitly solve this differential equation. What we can do is, again, repeat the procedure. So we compute another derivative, again, y prime in x0 plus h. This is f of x0 plus h, and for the other coordinate, we have to take y1 tilde and get again the slope of the tangent, and then we follow this slope of the tangent for some time. Usually the step size is always the same. So for h, for another h, so for another h, we come into x0 plus 2h. We move along the tangent and finish in this point. This is our another approximation, y2 tilde. And you see, again, we did some error. We jumped from the second solution in the family to third solution in the family, and so on. So we repeat this. So we repeat this procedure. And at every step, we jump from one curve to another. So this at every step we do some mistake, some error. This is called error in each step. Is called a local error. A local error. And then when we sum up the local errors in every step, we get a global error. So we have a notion of a local error. This is an error made in every step. But global error is the exact error compared to the true solution. So global error is usually bounded above by the sum of the absolute values of local errors. So global error, I will write it as GE. So GE is approximately, so it's bounded above by local error in the first step plus local error in the second step, and so on. It's sum of all local errors. Not LC, but LE would make more sense to write the local error as LE, not LC. So on this image, we see what is the local error. So in the first step, we have only the local and global error the same. So in the first step of our method, we have local error and local and global error the same. So this I will write with black will be local error. So in the second step, the local error is not the difference between our estimation and the actual solution, but only the difference between the second and third curve in the family. So only this is because if we solved our equation exactly with another initial condition, now the initial condition is that in x0 plus h, we should be in y1 tilde. But we did the error again, we switched curves. So the local error was this black one. So this is local error 2. However, the global error is the error to the first curve. So this is the global error. And so on. So if we continue, in every step, we have some local error. Only this is only the error made between the previous and the new curve. And the global error, which is the mistake between the initial curve, which is the true solution, and our solution after n steps. Of course, we are interested in the global error, but we can estimate only local errors. So analytically, we can estimate only local errors, and I will show you now this estimation. It's very easy to derive. But out of local errors, we will be able to also estimate the global error. So what's the actual algorithm for the Euler method, which is very easy? So algorithm. We choose a step size, h, and we repeat the procedure. So for I between 0 and, let's say that we do 100 steps to n. N is the number of steps. So for I from 0 to n, what we do, we compute xi plus 1 as xi plus h, and we estimate the next value of y. So y yi plus 1 is yi plus h times f of xi yi. So this is only the right hand side is only the formula for the tangent, and we compute the point on the tangent at xi plus 1 equals to xi plus h. So and we get our next approximation, and this is everything in the algorithm. So this is in fact Euler's method. Now I will show you that the error is quadratic in the step size. So the error in each step is quadratic. So it's proportional to step size squared. Why? Because we forget about all terms in the Taylor expansion of our function from the second on. So we have, let's say that our function f of xy is equal, our function, we are in fact searching for y. So we would like to find y, and we have y of x. Let's do a Taylor expansion. This is, so y of x plus h. This is y of x plus the first term in the Taylor expansion of y is step size over 1 factorial times the first derivative of y. And then the second term in the Taylor expansion is h squared or 2 factorial times second derivative of y with respect to x, and so on. So the third term is h cubed over 3 factorial times third derivative of y with respect to x, and so on. But you see that this y prime, this is f of xy. This is by definition, because our differential equation is y prime is f of xy. So we know what's y prime. And in Euler's method, we only take into account those first two summands of Taylor series, and we forget about the rest. And this rest is can be written as h squared times something, times some constant, plus h times some constant, plus h squared times some constant, and so on. And of course, we are only interested in small h's, because it doesn't make sense to do long steps. If h is big, then of course we will do big error. So it doesn't make sense to use this Euler's method for h which is big. So we can assume that h is very small. And if h is very small, then in this error, the most important part is this h squared c1. So for small h's, h squared times the constant c1 prevails. So prevails. So this remaining part is negligible in comparison to h squared times c1, because it's multiplied by another h. And we usually write this as big O of h squared. This means that the error is proportional to h squared, and the proportionality constant is given, so it's some c. So it exists and it can be determined. That's why, so the error in Euler's in one step of Euler's method is of size O, big O notation of h squared. This is of course local error. This is local error. That's why we say that Euler's method is order 2 method. What does this mean? So if we half our h, if we half the step size, the error, the local error will multiply by 1/4, will be 1/4 times times the previous local error. That's why we say that it's of order 2. But the global error, so this is the local error is of order 2, but the local error, the global error is O of h. Why? Because we are summing up local errors, and the number of steps is proportional to h. So if we are given our interval a to b, we're solving our differential equation on the interval from a to b. So a is x0, then b is x0 plus n times h. So number of steps times h. And now we can express here number of steps. So number of steps n is b minus a over h. So the number of steps is b minus a is a over h. This b minus a is given in advance. So this is these are the endpoints of our interval. So we are in fact summing up. So we have to sum up capital N local errors, each O of h squared. So altogether we have b minus a over h times O of h squared. So this b minus a is a constant which can be absorbed in this capital O, because capital O only says that the error is some constant times h squared. So this b minus a is then absorbed in this capital O, and this h from the denominator can be multiplied by h squared. So the global error is then capital O of h. So it's Euler's method. In general, it's linear in the step size, so it's not very accurate method. We have to really make a small h for Euler method to be accurate. But this means that it's computationally very demanding if we have to decrease h a lot, because then we will have to do a lot of steps. This capital N will be big. That's why Euler's method is practically not very, very useful. However, it is the basic idea of Euler's method is then generalized to Runge-Kutta method, which I will show you next hour. Is there any question? Was it clear? Okay, if no. Okay, so last hour we saw Euler's method as the basic method for solving differential equations numerically. The method is based only on approximating the solution by the use of the tangent to the curve, to the solution curve in the previous point. And of course, since following the solution is only taking into account the linear part of our function, the error is already in the quadratic part of the Taylor series. That's why the local error at each step is quadratic in the step size. Summing up over all steps, we see that the global error is then linear in the step size. So it's big O of H. We'll see on numerical examples today, and also next time there will be one very interesting example when we will work with systems of differential equations. We will see that Euler's method can be used also for systems, and we will see how we can get how those local errors can sum up together into completely wrong solution. So global error is becoming very high. But there is a solution to this non-practicality of the Euler's method. So I will just draw again the picture we started with. So let's say that this is our function y, which is a solution to our initial problem. So in Euler's method, what we did is only follow the tangent in the point x naught, y naught for some step size x0 plus h. How can we improve the accuracy of the method? Is to somehow take into account more derivatives, more tangents over this interval. So let's say that h is step size is fixed. And now we would like to take into account more slopes of the tangents over this interval x0 to x0 plus h. So we would like to approximate the average slope on the interval x0 to x0 plus h more accurately. So on the interval x0 to x0 plus h, slopes of the tangents vary. If you know what's the average slope, then we would get a completely correct approximation at x0 plus h. Of course, we cannot know average slope exactly, because this would require calculating integral of the function f(x,y), which is not doable. But instead of taking the approximation of the average slope only from the left, from the slope of the left endpoint, we can now use more tangents. So we choose more those, we compute more slopes in various points on the interval x0 to x0 plus h. So I draw 4 of them, and we take some average. So we compute the slopes of the tangents on interval x0 to x0 plus h in more points, and take their weighted average. It doesn't mean that all the weights are the same. So we can say that this green is more important than orange, is more important than black, is less important than violet, and so on. So we are the one who determine what is the weight of each of the tangents. So in take their weighted average, when we estimate the value of the next point, or of y in the point x 0 plus h. So you see that we have a lot of choices of tangents. We have a lot of choices of weights. Of course, we have to choose them in some meaningful way to ensure that the error will be small. But you can see that the choice is not unique. It's highly non-unique. So the methods which stem from these choices are called Runge-Kutta methods. It's a family of Runge-Kutta methods. So we get a family of methods which are called Runge-Kutta methods. There are many of them. There are a lot of them. You've seen in lab sessions, you've probably done this exercise this week at lab sessions, so-called Runge-Kutta method of order 4. One of the most well-known Runge-Kutta methods is the one of order 4, which means, what does this order 4 refer to? So you can think of this order. So when we had Euler's method, we said that the order of Euler's method is quadratic, because in each step we do an error which is quadratic in the step size. It's of order 2. However, since Runge-Kutta method of order 4, so it's of order 4, by definition, this means that the error is, which means that the local error is of order, is of size O of h to the power of 4. So this means that if we have the size of the step, then the error is multiplied by 1 over 2 to the power of 4, so 1 over 16. So it's much more accurate than the Euler's method. So let me show you which Runge-Kutta method of order 4 I mean, and then I will explain a little bit about the derivation. So this is this Runge-Kutta method of order 4. You see here for the average slope of the tangent, we take 4 points. So point xi, yi. So we are in point xi, yi, and now we move to xi plus 1, which is xi plus h, and we would like to compute yi plus 1. This is what we want to compute, and we take the average slope in the point xi, yi. So this is one slope, and then this is the first point. Then another point is xi plus a plus h over 2. So xi plus h over 2, and then yi plus k1 over 2, where k1 is already takes into account the previous point. So this k1 is some coefficient which already takes into account the derivative in the point xi, yi. So this is the second point. And then the third point, I won't write them down. So the third point is then again the same x coordinate and y coordinate changes, but this y coordinate is again, you see, it depends on the previous y. And then the fourth one is xi plus h, and then yi plus again k3, which depends on the previous point. So they are somehow connected. So we have point xi, yi. Out of this we determine next point. Out of this we determine next point, and out of this we determine next point. And now we take averages of the tangents in those 4 points. And we get, out of them, we get the average slope of the tangent. And the weights are 1, 6 over 6, and then 2 over 6, which is 1/3, then 1/3, and 1 over 6. So the error at each step, it's sorry, before I said that the local error is of order O of h to the power of 4. In fact, it's O of h to the power of 5, and the cumulative error, so the global error, is O over h to the power of 4. So, and now, how would one guess that the coefficients k1, k2, k3, k4 are exactly as written here? And how would one choose those 4 points? Okay, now I will switch to some handwritten notes in Slovene. For those who don't know Slovene, it's not a lot of text. Mostly there are derivations, so you will be able to understand them. So this is the Runge-Kutta method. So we have our function, and our function, writing our function, we would like to estimate the next point. Here I will explain, let's say, Runge-Kutta method of order 2. So we would like to express, to approximate next y based on the previous y, and then on we take into account tangents in 2 points. So in the point which is the left end point of our interval, and then some point in between. And those b1 and b2 are coefficients, so are weights. So b1 plus b2 are sum up into 1, and they can be some positive weights. So if we take b1 equals to 0 or b2 equals to 0, then this means that we will take into account only slope of the tangent in one fixed point. We would like that our method is of order, let's say if we have 2 conditions, we would like that it's of order 3, which means that if we expand our approximation in the Taylor series, we can demand that the first 3 terms will be correct. So we have our function y. As before, we can extend it into its Taylor series. It's written here. So y in the next point, it's y in the previous point plus step times the derivative, which is just f, plus h squared over 2 times the second derivative. And here I've used, since the first derivative is the function f, and this function is depends on x and y. So then I took the derivatives of the function f. This is the second derivative of y. I used the chain rule because this f is in fact a function of x and y of x. So I've used chain rule to compute this second derivative. And on the other hand, since I will use two intermediate points, I can also use Taylor series in two variables. So this f of x, y, this is a function of two variables. We can also write Taylor series for a function of two variables. It's written here. So it generalizes naturally. So Taylor series from one variable generalizes to functions in two variable in a natural way. And this is what we use here. So we on one side, we express, so we extend y into the Taylor series of one variable, and on the other side we express the function f, which is a function of two variable, again into the Taylor series for functions of two variables. And when we do this, we get on left side we get something, on the right side we get something, and you see on left side we get something which doesn't depend on h, something which depends on h times some coefficient, then we get h squared times some coefficient, and so on. And the same on the right side. And since we want that our method is of highest possible order, so if we have two conditions here, then we can demand that it's of order 3. So the first three coefficients in this on both sides are the same. We have here three conditions. So the coefficient at 1 must be the same. So this is yn. This is the same. And then the coefficient at h on both sides should be the same. So on one side we have f of n, and on the other side we get b1 times f of n plus b2 times f of n. And we can also demand that the coefficient at h squared is the same on both sides. Out of those, you see, we get two equations in a few unknowns, b1, b2, c, and a. So we have two equations and four unknowns. It's natural to demand that b1 plus b2 is 1 because b1 and b2 are weights. So it's natural to demand also that the sum of b1 and b2 is 1. But then we still have three equations in four unknowns. So the solution to this is one parametric, which means that Runge-Kutta, there is a one parametric family of Runge-Kutta methods of order 2. So if we take a Runge-Kutta method and we say that we will take the weighted average of slopes of tangents in 2 points, then there is a whole one parametric family of possible choices of such Runge-Kutta methods of order 2. So here we have two of them. So for example, if we take b1, b2 equal to 1/2 and c and a equal to 1, we get one Runge-Kutta method of order 2. If you take b2 is equal to 1, b1 is equal to 0, and then c and a equal to 1/2, then we get another possible Runge-Kutta method of order 2. Both of them are of order. So in both of them, the local error is of size O of h cubed. But the specific constant in this big O notation depends on the function f. So for some functions, one of the methods could be better. For some other functions, the other method could be better. We cannot know for sure from the general rule. So this was the idea behind the derivation of Runge-Kutta method when we take into account two tangents. So the basic idea is to expand both sides in Taylor series. On one side, we use Taylor series of one variable. On the other side, we need to use Taylor series of two variables. And we see that even here in the simplest case of Runge-Kutta method, where we take only two tangent vectors, the derivation is quite technical and quite a lot of work. We have to be careful. But for a general Runge-Kutta method, when we take into account more tangents, those methods require even more calculations, but the basic idea is the same. We expand both sides in the Taylor series, and then we try to make equal as many coefficients at h as possible. So the general Runge-Kutta method is of this form. We have S slopes and S coefficients, and then we have to compute those coefficients so that the Taylor series will be equal up to some term.
So the order of Runge-Kutta method tells us how many tangents have we taken.
Yes, exactly. Yeah.
Okay.
Okay, so, and this Runge-Kutta method of order 4, one of the possible choices, which is many times used, is that one, which stems out of this system I've just explained. But this is not highly non-unique. So there, even in Runge-Kutta methods of order 2, we had one parametric possibility of solutions for the actual coefficients. However, if we increase the number of tangents we take into account, then the dimension of the space of solutions is growing with every new tangent. So we won't go into the derivation of these formulas, but this is the idea behind them. So the error at each step of Runge-Kutta method of order 4 is of size h to the power of 5, O of h to the power of 5. So the cumulative error is then O of h to the power of 4. The same, by the same reasoning as for the Euler method, because we are doing n steps, and n is equal to b minus a over h. So n times O over h square, h to the power of 4 is O to the power of, no, n to the is n times O to the power of, n times O of h to the power of 5 is O of h to the power of 4. Okay, let me show you now one example. So also Runge-Kutta method is very easy to implement. In Euler's method, we have only K1, but in Runge-Kutta's method, we have to, in every step of the for loop, we have to compute 4 Ks. So it's computationally more demanding, but it's easy to implement. It's worth, so this computational power, additional computational power is worth doing because we gain a lot on the cumulative error side. So let me show you an example. So here we have the differential equation, first order differential equation, y prime is minus y minus 1. And we will be solving it on the interval from 0 to 1. We will do 30 steps, and the step size will be 0.1. I didn't show you the script for Euler method. You see, Euler method is very easy to implement. We give it a function, initial x, initial value of y, number of steps, and step size. And it does what we saw on the slides. And Runge-Kutta method needs the same arguments. However, in every step of the algorithm, it does 4 calculations, not only 1. Okay, let's return to this example. So we have this equation y prime is minus y minus 1. What is the actual solution of this differential equation? So it's a separable differential equation. So the actual solution is, in fact, you can do it by yourself, but y is 2 times e to the power of minus x minus 1. So y prime is minus y minus 1. The solution to this is here, 2 e to the power of minus x minus 1. You know how to do it. It is, in fact, separable differential equation, so you know how to solve it analytically. And here I will show you the approximation with using Euler's method once, and then the approximation using Runge-Kutta method once. And we will see that the Runge-Kutta method is much more accurate. So let's run this example. So first, here we have the solutions. So in the point, we start in the point x equal to 0, and the initial point is y equals to 1. And in the initial point, of course, the error is 0. And then we do step size 0.1. We compute by Euler's method new approximation for y, and we get 0.8. Since we know what's the analytic solution to our equation, we can compute the error. And the error you see is on the fourth decimal place. And so on. We continue by step sizes 0.1 up to the after 10 steps we come into point 1, and in point 1 you see that local errors sum up together. So at the end the global errors is already on the 2nd decimal place. So each local error is on the 4th decimal place, but they sum up together. So at the end, it's on the 2nd decimal place. So it's Euler's method is not very accurate. However, Runge-Kutta method of order 4, you see, is much more accurate because the errors at the beginning, the error is on, I think, the 7th decimal place. And at the end, the global error is still on the 7th decimal place. So it's much more accurate than Euler's method. And here I can show you also the figures. So this is the direction field. We have seen this direction field already last time. So those are vectors, directions of the tangents at every point. So y prime is minus y minus 1. It's computed in some grid, and in every point of this grid, the tangent, the slopes of the tangents are drawn. So the solutions are in fact following those directions. So we can see from this direction field what is the solution of this equation, and it looks like an exponential function with a negative coefficient in the exponent. And here we have the solution. The blue one is the exact solution, and the red one is the solution by Euler's method. And you see, since we start in the left-hand point, here the error is small, but then they are more and more apart. Here is the actual global error using Euler's method. So at the beginning it's 0, then it grows, then it starts to be smaller. So we estimated global error as the sum of absolute values of local errors. But here, the actual global error doesn't really need to increase all the time. So here, the local errors were, for example, negative. That's why they were summing up into the global error. But then from here on, the local errors become positive. So they in fact decrease the global error. But this is only in this specific example. When we do the estimations, we can only estimate the global error by summing up absolute values of local errors. And let's look on the graph for Runge-Kutta method. You see here, we cannot even see with bare eye that exact solution and Runge-Kutta method differ, even if I increase the picture, it's still we still cannot see the difference between both solutions. But if we look at the graph of the error, we see that it's 10 to the it's 10 to the power of -7. That's why we can see the difference between the solution using Runge-Kutta method and the actual solution. So global error is of size 10 to the power of -7 all the time. Okay, the next thing is to study systems of first order differential equation, and we have only a few minutes left, so we won't go into this. I will only explain you the function ODE 4,5 in MATLAB. So this function ODE 4,5, it is one of the methods to solve differential equations in MATLAB, and this function combines, so it combines two Runge-Kutta methods. One of order 4 and one of order 5. And it is much quicker than the usual Runge-Kutta method of order 4. And why it is much quicker? Because this method is better than Runge-Kutta method 4 above, because it changes, it adaptively changes the step size. So if the step size is too big, so if the error is too big, then from some point on, it makes it half and continues with half of the size of the previous step. But if it's okay, then it can also increase it, and that's why it's quicker. So we come to the right end point quicker than with a fixed step size, because in the usual Runge-Kutta 4 method, the step size is fixed, and if the final approximation is not good enough, we have to compute everything again with a smaller step size. However, this ODE 4,5, it's called, the actual name for this method is Dopri 4,5. So this method is adaptive method because it can compute few approximations up to some point with some step size, and then changes the step size only from some point on. And how does it do this? Let me just find the proper slide. Yeah, so the idea is to take into account two methods, two two Runge-Kutta methods. So for example, we have here Runge-Kutta method of order 4. Here are the coefficients for those method, for this method. So this is our method, only the coefficients are collected in a table, otherwise it's the method from the slides. But then we take another Runge-Kutta method with the same coefficients here. So with the same coefficients here, only the weights here are a little bit different, so are changed. So instead of the last row is different. And why is this so? Because then we can subtract those two approximations. So we compute approximation based on one method, and then approximation based on the second method with different coefficients. And when we subtract them, then we can estimate the error out of those or out of this difference. And if the error is small enough, we accept this step and continue. But if the estimation of the error is too big, then from that point on, we make h smaller. Usually we take h over 2, or this method takes h over 2 and continues with smaller step size. So this is basically the idea behind this method. But if you use this method in MATLAB, then you use it by calling the function ODE45. And this is the most widely used method, in fact, DOPRI45 with this function name. So this is the most well-known used method implemented in MATLAB and other differential equation solvers. This is all for today. Are there any questions? Okay, if not, then next time we continue with systems of first order differential equations. In fact, we will generalize all what we did for one equation to systems of differential equations. In fact, we will see that Euler's method and Runge-Kutta's method, in fact, work in the same way, only that y's and f's must be vector functions. But all the derivations are the same, and also the implementation is the same.